Water is not from Earth. Watts. Water is not from Earth. Water is the only alien. Water is an alien. Watts. Water is electricity. Water is not from Earth.
Scientists have looked long and hard into the origins of Earth's water, and what they've found is amazing. Our planet shouldn't be wet at all.
The place where the Earth is right now seems very dry. So if the Earth formed as a dry rock around a hot young star, then how did this water get here?
Every possibility has problems, and we want to know the answer.
Tracing the exact source of Earth's water is surprisingly complex. The journey starts over 4.6 billion years ago, during the formation of our solar system. A vast cloud of gas and dust hangs in space. Inside this cloud, atoms of hydrogen and oxygen proliferate.
Oxygen is one of the most abundant atoms in the universe. Hydrogen is the most abundant atom in the universe. You're going to get a lot of whatever it is they form.
Over millions of years, these highly reactive atoms bind together to form H2O, water.
Water is a fairly simple molecule. It's made of 2 hydrogens and 1 oxygen.
Soon the universe had lots of water. Icy, dusty, spread out water. But how did it get to Earth? Scientists have a few different theories, but they all have some problems. And we still don't really know how to account for those problems. One theory is based on the idea that as this icy dust swirled around, it would have condensed and collided into bigger rocks and meteorites and even rocky planets like Earth. So it's possible the water ice was part of the matter that crashed together and created our planet in the first place. And what if it never left? At first, the planet would have been incredibly hot, and water on the surface would have evaporated right back into space. But these scientists think that some water stuck around, or that there was water that seeped up to the surface of the planet as the Earth cooled. After around
Chemistry of water. Water is an inorganic molecule that is the most important compound in the body. In fact, a normal adult's body weight is made up of 50% or more of water. A molecule of water has 1 oxygen atom covalently bonded to 2 hydrogen atoms. Covalent bonds being the chemical bonds that are formed by the sharing of 1 or more pairs of electrons by the outer energy levels or shells of 2 atoms. Water molecules are also polar molecules. Even though the oxygen atom shares electrons with the hydrogen atoms, the electrons are not shared equally within the molecule. This gives the oxygen side of the molecule 2 partial negative charges, and each of the hydrogens a slightly positive charge. This means that each water molecule can form up to 4 hydrogen bonds with adjacent water molecules. Hydrogen bonds are the result of an unequal charge distribution on a molecule. These molecules are said to be polar. This property allows water to act as a very effective solvent, which means it is able to dissolve or break apart many other substances. Substances that do dissolve or break apart in water are called hydrophilic, which means water-loving. Nonpolar substances that do not dissolve in water are called hydrophobic, or water-fearing. Some substances, such as glucose molecules, dissolve and remain intact in water, as water molecules surround the substance, forming a hydration shell around the molecule. Some substances dissolve and dissociate or break apart in water. Table salt, or NaCl, when added to water will dissociate to form positive sodium Na ions and negative chlorine Cl ions, with hydration shells forming around each ion. This property of water allows it to function as a transporter, as water-based fluids, such as blood, transport substances dissolved in water throughout the body. Non-polar hydrophobic substances, such as fats and cholesterol that do not bond with water, must be enclosed within a transport protein molecule to be transported within blood. And that be the basics of the chemistry of water.
We first need to understand how rivers work. Rivers of many sizes occur in the UK, and the volume of water carried, even in the smallest, is astonishing. This relatively small river transports a road tanker's load of water every second. In times of flood, that can become as much as 5 tankers every second. Rain seems the obvious reason why rivers continue to flow, day in, day out. But days or even weeks can go by without any rainfall. So why do rivers flow during these times? The answer lies back upstream. The land that a river drains is called the catchment, and a river of this size could collect the rain that falls on an area of several hundred square kilometers. The amount of rain that falls in Britain varies greatly from place to place, from only half a metre a year in areas of southeast England to as much as 4 metres a year in parts of Scotland. The amount also varies throughout the year. The fate of each drop of rain depends on where and when it lands. Some of the rain evaporates back into the atmosphere from the surface of plants. Water hitting the ground can also evaporate, as well as soak into the soil. Once in the soil, it can be used by plants before being passed back into the atmosphere. Large plants, like fully grown oak trees, can use as much as 400 litres a day. Some of the rainfall will also move off downhill. This is known as runoff. The amount of rainfall that becomes runoff depends on how much rain there is and when during the year it falls. It also depends on the type of land on which it falls. Ploughing, for example, will reduce runoff by holding up the water, allowing it to soak into the ground. Runoff will be greater on bare soil, and greater still where land is built on. In upland areas, where slopes are steeper and the soils are often thin, a lot of the rain runs off straight into rivers, and so these rivers rise and fall rapidly with every rainstorm. When the amount of rain falling is more than the river can carry away, the inevitable happens. Runoff is one way for water to reach the river. But if this was the only way, then rivers would dry up when the rain stopped. This doesn't happen, so there must be some other source of water.
Coexisting and interacting with each other already. The question is, what happens Takashina's own interest in the effect didn't start in the kitchen.
A friend of mine emailed me a link to this paper in Physical Review Letters by Heine Lincoln,
entitled Self-Propelled Leidenfrost Droplets. The paper reported a way to move beads of water across a heated surface covered with stair-like ridges. As the droplet encountered a ridge, the flow of vapor beneath it pulled it up and over, even when the surface was on a slight incline. With no moving parts, the process could potentially be used to cool an overheated microchip inside of a computer.
and it looked so interesting. I mean, you have to try it, right?
So Dr. Takashina and a group of physics undergraduates at the University of Bath got to work building and testing different ridged blocks. Right off the bat, the team noticed
The sharper the teeth are, the deeper the angle they seem to be able to climb.
and this led them to wonder what else would affect the droplet's ability to climb.
So at very high temperature, the droplets become completely levitated. And there, they can't climb very steep inclines at all. The steepest angle they climb is achieved at a lower temperature.
Here the droplets weren't 100% levitated. They still had contact with the surface, and this allowed them to grip its teeth. But as the team started using temperature to precisely control the ascent of the droplets, they noticed
that depending on the temperature of the block, the water would move in different directions. And this is completely unexpected.
and really cool. When the surface was heated over the Leidenfrost point, the droplets curved to the left. If they were under, they veered to the right.
There must be something in the structure of the surface
Upon magnifying the ridges, the team noticed that they had small grooves.
which we think is responsible for the directionality.
And as one might expect from a team of undergraduates, a creative idea took hold.
If you arrange the blocks in the right directions and you put the walls in the right places, it will work.
Behold, the Leidenfrost maze.
A bubble is just some volume of gas surrounded by liquid. It can be surrounded by a lot of liquid, like in champagne, or just a thin layer, like in soap bubbles. So why do these bubbles have any shape at all? Liquid molecules are happier wrapped up on the inside, where attraction is balanced than they are at the edge. This pushes liquids to adopt shapes with the least surface. In 0G, this attraction pulls water into round blobs. Same with droplets on leaves or a spider's web. Inside thin soap films, attraction between soap molecules shrinks the bubble until the pull of surface tension is balanced by the air pressure pushing out. It's physics.
Physics is great, but mathematics is truly the universal language. Bubbles are round because if you enclose the maximum volume with the least surface area, a sphere is the most efficient shape.
Yeah, that's another way of putting it. What's cool is if we deform that bubble, the pull of surface tension always evens back out to the minimal surface shape.
Water is not from Earth. Water is the watts. Water is electricity. Water is not from Earth.